All right, starting with problem 2. Wheat is poured through a chute at a rate of 10 cubic feet per minute and falls in a conical pile whose bottom radius is always half the altitude. So there's a lot of craziness in there that we have to unpack. So we have this stuff falling on the ground. And it's going to form a pile in the shape of a cone. Okay, the radius at the bottom, is h for height. The radius at the bottom is always half the altitude or height, right? So radius is 1/2 h, right? It's being added at a rate of 10 cubic feet per minute. That's a rate of change of volume. So we're given that dV dt is 10. And then our goal, how fast will the circumference of the base be increasing? So find dC dt when the pile is 8 feet high. So when h equals 8. Okay, so we're going to start with the formula for volume of a cone. Since this is a review, it's not given, but on an exam it will be. So 1/3 pi r squared h. Okay, and I have dV dt. I want to find dC dt. I don't see c anywhere in here. So maybe what I want to do is say, all right, well, what does volume have to do with circumference? Well, let's look at circumference. For the base, circumference is 2 pi r. Okay, so I could solve this for r, something like that, and plug back in. Or another way to look at this is, okay, if I differentiate this, dc dt equals 2 pi times dr dt. So if I know what dr dt is, I can plug it in to get dc dt. Okay. Well, now if I come back here to my volume equation, I can say, all right, what I really want is dr dt. Okay. So in this case, I don't want the h, so let's eliminate the h. So if I multiply both sides by 2, 2r equals h. Okay, so volume is 1/3 pi r squared times 2r. So volume is 2 pi over 3 times r cubed, right, grouping the r's together. And now we differentiate. So dV dt is 2 pi over 3 times 3r squared times dr dt. Okay. Now to solve for dr dt, I need to plug in r and dV dt. I do have dV dt, but I don't have r. I have h. So I come back over here and say, okay, well, maybe I'll use this one. I need to find r when h is 8. So r is 1/2 times 8, or 4. Okay, so I plug that in. dV dt is 10. The 3's cancel. R is 4. Okay, divide to get dr dt by itself. 4 squared is 16 times 2 is 32. So 10 over 32 pi equals dr dt. And now I'm going to take that and plug it in up here. So dc dt is 2 pi times 10 over 32 pi. Do a little bit of canceling. Pi's cancel. This 2 will cancel to make this a 16. Cancel here to make this an 8. So I end up with dc dt equals 5/8. Okay. All right. Any questions on that one? move on. Problem 3, find the linearization of f of x equals tangent x at x equals pi over 4, and then use this to approximate tangent of pi over 4 plus 0.1. All right, so first of all, for a linearization, you can either remember a formula or you can just say, I'm finding the equation of a tangent line. Okay, so it's at this x value, so my y value is going to equal f of pi over 4, which is tangent of pi over 4, which is 1. Right, so I have the point pi over 4 comma 1. Then I need to find the slope, so we get f prime of x. Okay, the derivative of tangent x is secant squared x. So the slope is f prime of pi over 4, which is secant squared of pi over 4. And I like to think of secant as 1 over cosine when I'm plugging in, because I know cosine of pi over 4 is root 2 over 2. Okay. When I square that, I'm going to get 2/4, and 1 over 2/4 is the same as 4/2 or 2, so the slope is 2. Okay, so here I can start with finding equation of a tangent line, y minus y1 equals m times x minus x1, and plug in. Y minus 1 equals 2 times x minus pi over 4, and then add 1 to both sides. Okay, if you remember the formula from section 4.2 for linearization, it says that L of x is f of a plus f prime of a times x minus a, and that's what we have right here, right? So this is f of a, right, that we added over after a step. This is f prime, slope, and then x minus the a. Okay, all right, so this is L of x. So find the linearization, check. Okay, next we're going to use this to approximate tangent of pi over 4 plus 1. So tangent of pi over 4 plus 0.1 is exactly equal to f of pi over 4 plus 0.1, and I approximate the function with the tangent line, the linearization. So this is approximately equal to L of pi over 4 plus 0.1. And for L of pi over 4 plus 1, I plug into this formula. I have 1 plus 2 times pi over 4 plus 0.1 minus pi over 4. Okay. Pi over 4 and negative pi over 4 add to 0. So I have 1 plus 2 times 0.1, or 1.2. Okay. Problem 4, use a linear approximation to estimate the cube root of the, oh, we did this one in class, so I'm going to skip over this one. 5, find the absolute maximum and minimum value of this function on this interval. Okay. So the first thing we want to do when finding a max and min is to find the critical points. So we're going to take a derivative, and maybe before I take a derivative, it's a good idea to rewrite this as sine of x squared plus cosine x, so that it's very clear on what order I'm chain ruling things in. Okay, so sine x is the inside function. Stuff squared is the outside. So when I differentiate, I get 2 inside function to the power of 1 times the derivative of the inside function. And then the derivative of cosine x is negative sine x. Okay. So I want to find out where f prime is equal to 0 and where f prime is undefined. There's nowhere where this is undefined. Right? There's no fractions. There's no, and nothing where I could get an undefined value. So let's look at this thing equal to 0. So I have 2 times sine x times cosine x plus negative sine x equals 0. And when I have an equation equal to 0, I always want to see if I can solve by factoring. And in this case, a sine x is the only thing that really factors out. But I think that's going to be enough. So when I factor out a sine x, I'm left with 2 cosine x minus 1. So I can set the factored pieces equal to 0. So sine x equals 0, 2 cosine x minus 1 equals 0. Okay, and I'm going to solve those. For sine x equals 0, I get x equals sine inverse of 0 plus 2k pi, which is 0 plus 2k pi. Okay. Or I get x is pi minus that value, which is just pi. All right. Now, the interval negative pi to pi is 2 pi long, right? So if you find a value inside and you add 2 pi, you'll be outside, or if you subtract 2 pi, you'll be outside. So out of these two, the only things that are going to be in between negative pi and pi are, from this first one, I'll get a 0, and from the second one, I'll get a pi. The other values are either going to be too big or too small. Okay, so I get 2 values so far. Now let's go solve this cosine equation. So 2 cosine x equals 1. Cosine x is 1/2. So x is cosine inverse of 1/2 plus 2k pi. Or x could be negative cosine inverse of 1/2 plus 2k pi. Okay. And remember, at this point, if you don't have your unit circle memorized, now's not the time to start. Use your calculator, make sure it's in radians, and you plug in cosine inverse of 1/2, and you should get pi over 3. Maybe you have to factor out a pi or something like that to find that. So we'll get x is pi over 3 plus 2k pi, and x is negative pi over 3 plus 2k pi. Okay, so in the negative pi to pi range, pi over 3 and negative pi over 3 are going to fit. And nothing else. Okay, so now what I'm going to do is I'm going to make a chart with my endpoints, so negative pi and pi, and then all of the critical points that happen to be in between these, right? So negative pi over 3, 0, pi over 3. Pi here is counted twice, but that's not... I suppose on this one, if I subtracted 2 pi, I'd have negative pi. But again, the endpoints are already counted, so I don't need to worry about that. Okay, I'm plugging into the original function f of x, not into f prime. And although I think that I can get an exact value for every single one of these, I don't really want the exact value as much, because it's going to be more difficult for me to see which one's the biggest and which one's the smallest. So I'm going to get a decimal approximation for all of these. Okay, so let's start by plugging this into my calculator. Plug the function in. Okay, there's y1. All right, we put in sine of x, which is then squared, plus cosine x. All right, so I go to variables, y variables, function, y1, and we'll just plug each one in one at a time. So when I plug in negative pi, I get negative 1. Okay. And I'll put in negative pi over 3 and get 1.25. When I put in 0, I'm going to get 0 plus 1. Okay, let's put in positive pi over 3. I get 1.25, and then positive pi, and I get negative 1. Okay. On this list of outputs, 1.25 is the max. Okay, on this list of outputs, -1 is the min. Both of these occur at more than one spot, okay, but the max is the y value. Right? Likewise, the min is the y value. Okay. Any questions on this one? Okay. Let's move on to problem 6. Find the absolute max and min of f of x is x cubed minus 9x plus 1. This one doesn't have trig stuff in it, so it's probably going to be a little bit easier than the last one. So I'm going to start by finding the critical points. F prime of x is 3x squared minus 9. So let's figure out where f prime is equal to 0. I have 3x squared minus 9 equals 0. Okay, so 3x squared equals 9. X squared is 3. So x is positive or negative root 3. Okay, this is an absolute max and min on a closed interval again. Negative root 3 is smaller than or to the left of -1. So when I make my chart, it's not in between -1 and 3, but positive root 3 is. So I'm only going to check these three values. I'm not going to use the negative root 3. Okay, and once again, I'm going to just find some values on my calculator. So we have x cubed minus 9x plus 1. Okay, and again, when I'm finding a max and min, I'm looking at the original function, not the derivative. Okay. So we put -1 in. I get 9. Put in root 3, and I get negative 9.392. Put in 3, it looks like I'll get 1, but I don't trust my mental math, so let's just check it. Okay, so 9 is the max, negative 9.392 is the min. All right. Moving on to graphing. This is a little bit more than graphing. I like to think of this as like analysis of a function. All right, so first step, find the intercepts. Okay, so for y-intercept, that's the y value when x is 0. So I plug 0 into the function, and I get 0. Okay. For the x-intercept, I want to figure out where is the function equal to 0, right? Plug in 0 for y and solve for x. So I have x squared over 1 minus x cubed equals 0. A fraction is 0 when the numerator is 0. So I get x equals 0. I get the same point. Okay. So 0, 0 is doing double duty. It's the only x-intercept and it is the y-intercept. All right, find the horizontal and vertical asymptotes. So let's start with the horizontal. I want to take a limit as x goes to infinity of my function. Right, that's how I find horizontal asymptotes. I'm looking at the end behavior as x goes off to infinity. So this is the limit as x goes to infinity of x squared over 1 minus x cubed. And if you want to, you can use L'Hopital's rule on stuff like this, and that's fine. if it's polynomial over polynomial, you can go a little bit faster if you just divide by the biggest thing in the denominator. So x squared over x cubed, 1 over x cubed over x cubed. So I'm going to get 1 over x on top and 1 over x cubed minus 1 on bottom. And the point of that is that if I have 1 over x to any power, as x goes to infinity, that fraction is going to go to 0. Because I'm dividing by bigger and bigger numbers, right? So the whole thing's going to get closer and closer to 0. Look at 0 over 0 minus 1, which is 0. So y equals 0 is the horizontal asymptote. Okay. Now let's look at the vertical asymptotes. For vertical asymptotes, we just want to know where the denominator of the original function is equal to 0. So we take this 1 minus x cubed and set it equal to 0. So 1 equals x cubed, cube root both sides. So I get x equals 1. So y equals 0 is the horizontal asymptote. X equals 1 is the only vertical asymptote that we end up having. Okay. Okay, now we have our intercept. All right, next we want to find out the x value of the relative extrema and the intervals of increase and decrease. So parts C and D we can do at the same time with that first derivative test. Okay, and the derivative is already computed and simplified for us, so we're going to make use of that. Okay, let's do this up here, C and D. So I want to start by looking at where is f prime equal to 0, and then where is f prime undefined. Okay, f prime equal to 0, that's going to be where the numerator is 0. So if I factor in x, I get x cubed plus 2 times x. So x equals 0, x cubed plus 2 equals 0. X cubed is negative 2, so x is the cube root of negative 2. You can take cube roots of negatives, that's fine. Okay. F prime is going to be undefined when the denominator is 0. So that's where 1 minus x cubed is 0. And we already solved that earlier. That's where x is 1. So I end up with these 3 critical points. Okay. So when we do our first derivative test, I'm going to make a number line, and I'm going to put these 3 numbers on here. So I have the negative cube root of 2, 0, and 1. And I'm going to test something from each of these intervals into f prime. So I need something to the left of the cube root of negative 2. So I'll just pick negative 3. That's very safely to the left of there. Okay. So in the numerator, if I put in negative 3 to the 4th power, I think that's 81. Negative 3 times 2 is 6. Right, so 81 minus 6 on top. And I have 1 minus 27, which is then squared on bottom. Okay, so I get something like 75 over 676. I don't care exactly about the number. The point is that it's positive, so my function is increasing. Okay, something between negative cube root of 2 and 0, I'll put in negative 1. Okay, into f prime. So negative 1 to the 4th is 1, minus 2, and then I have 1, and then negative 1 cubed is negative 1, so minus a negative 1 is plus 1. So I've got negative 1 over 2 squared, which is 4. So I have a negative, so the function is decreasing. Okay, in between 0 and 1, there are lots of choices, but none of them are whole numbers. So I'm going to plug in a half. Okay. Okay, so if I plug a half in the numerator, I get a half to the fourth plus 2 times a half. So, you know, I get, what's that, a 16th plus 1, so 1 and a 16th or something like that. Okay, but it's positive. In the denominator, when I put in a half and cube it, I'll get 1/8. 1 minus an eighth is a positive number. Squared is positive. So, you know, plug in my calculator, I get, 0.765, but, again, it's positive, so we're increasing here. And then something bigger than 1 I can plug in, and maybe a 2. Okay, so in the top I get 20, and the bottom 1 minus 8 is negative 7, but squared will give me a positive 49. Positive over a positive is positive. All right, so that's my increasing, decreasing intervals, which answers part C. I can see that at negative cube root of 2 it goes up and comes down, so we have a max, a relative max. And then at 0, it goes down and then comes up, so we have a relative min. Okay. So that answers part D. Something that wasn't, that didn't come up, but I want to point out, is that at 1, we had a vertical asymptote. Okay, so 1's not defined in the original function. So even if at 1 it went up and came down again, that wouldn't be a max. 1 can't be, x equals 1 can't be the location of a relative max or a min, because it's not defined in my function. Okay. Let's move on to parts E and F. So just like C and D went together with that first derivative test, parts E and F, we're going to do the test for concavity using the second derivative. Okay, so first thing to do is figure out where the second derivative is 0. So I set the numerator equal to 0, and then where it's undefined, I'll set the denominator equal to 0. So 2x to the 6th plus 14x cubed plus 2. Double check, make sure I got that right. Okay. Now, this might be a little bit challenging to solve because it's a 6th degree polynomial, but if we did a little substitution here, right, if I say let z equal x cubed, then this is 2z squared plus 14z plus 2, and it looks like a quadratic now. Okay, so z is the opposite of 14, plus or minus the square root of 14 squared, minus 4 times 2 times 2, all over 2 times 2. Okay, so 14 squared for that one, 169. And 4 times 2 times 2. Okay, so 169 minus 16 is 153. So we get negative 14 plus or minus the square root of 153 all over 4. I think that it might be beneficial for us at this point to just get a decimal approximation, because I have to go back and plug this in for z and then solve for x. So we're going to end up cube rooting this, and this is already kind of a mess. So I'm going to go ahead and get decimal numbers for this.
Wait, I have a question.
Yeah.
Didn't you say 14 squared was like 196 or something like that?
Yeah.
So where did you get the 161?
I don't know. Let me try that again.
Okay.
Yeah, 14 squared is 196. And 196 minus 16 gives me 180, not 153. So I'm going to blame a glare on my calculator, but that's just me not being careful. Thank you. Okay, same deal. We're going to plug this in to get a decimal approximation. Okay. So I get that z could either be negative 0.1459 or z could be negative 6.8541. So now solving for x, so I get x is the cubed root of this first one, which is negative 0.0486, or x could be the cubed root of this second one, which is negative 2.2847. Okay. So make our number line. Oh, I'm sorry. We also need where f double prime is undefined. And one of the things you'll notice here is that that 1 minus x cubed, right? So, when you set it equal to 0, x is 1. That keeps showing up just with higher powers as the derivatives goes up, right? So that vertical asymptote ends up, showing up in both the first and the second derivative. Okay, so we have negative 2.2847, negative 0.0486, and 1 as our critical points for the second derivative. So we have to test something in between. The only good news there is it's a lot easier to find integers when your critical values aren't. So we'll plug in, start with, say, negative 3. I'm plugging into f double prime. And what I'm going to do is on my calculator, I'm just going to plug this thing in. I'm going to plug that whole mess into my calculator. Okay, so coming back down, when I plug in negative 3, my calculator is going to output a positive 0.049, right? So it's positive, so that means it's concave up here. When I put in negative 1, I get negative 1.25, so it's concave down. In between this negative and positive 1, I can put in 0. I get 2. That's positive, so it's concave up. And then bigger than 1, I can plug in something like 2. And I get negative 0.705. That's negative, so it's concave down. Okay, so that means that the graph changes concavity at both of these critical points, so they're inflection points. Changes concavity at one, but just like we discussed a minute ago, because that's not a point on the graph, that's not an inflection point. Okay, so we have our intervals of concavity, and we have our inflection points. So that's parts E and F. The final step is going to be to graph this thing. So let's go ahead and set up our graph. And what I'm going to do is underneath my graph, I'm just going to take the information that I already found and just transcribe it over. So we had these critical points. The negative cube root of 2 is negative 1.26. Okay. So I know that 1 is an important number. I have okay. So we have negative 1.26 and 0. So up, down, up, up. Okay, and then for the second derivative, negative 0.04 and negative 2.2 were important. So I'm going to throw those in there as well. Okay, so in between here and 0, that was all decreasing, so it's decreasing here too. And I threw this guy in, but to the left of negative 1.26, it was always increasing. Okay. All right, now I throw in the concavity. It's concave up until I get to the negative 2.2. Then it goes concave down until I get to the negative 0.04. Then it switches to concave up until I get to 1. And then it switches to concave down. All right, let's put in our asymptotes. We get a vertical asymptote at x equals 1, horizontal asymptote at y equals 0. You are allowed to cross horizontal asymptotes, which is good because our graph actually hits it here. Y-intercept is 0, 0. Okay, so we put in our 0, 0 from part A, our horizontal and vertical asymptotes from part B. Part C and D gives the increasing, decreasing. E and F give us the concavity. So I think we have all of our remaining information summarized down here. So let's just go ahead and start graphing this thing. I like to start with a point that I actually have. Okay, so at 0, right, we have this point. If I move to the right, it is concave up and increasing. So I have to draw the increasing side of concave up, and we need to approach our asymptote and hit this point. If I keep moving to the right, I have two asymptotes that I need to approach. It's concave down and increasing. So this is the increasing side of concave down. As I go to the right, it needs to approach the horizontal, so I can't go over it because I'm not allowed to come back. And as I go to the left, it needs to approach the vertical asymptote. Okay, going back to my 0, 0 point and moving left, I have this concave up and decreasing. So we have a shape like this, okay, until we hit this, 0.04 business. Okay. And then between the 0.04 and the negative 1.26, it's concave down and decreasing. So this is the decreasing side of concave down. Okay. Sorry, that's going to go up to here, to the 1.26. Between negative 1.26 and negative 2.28, it's increasing and concave down. So I want the increasing side of concave down. Okay. And then from this point to the left, it's increasing and concave up. So I want a shape like this. I need to join in with this spot, and I need to make sure I'm approaching my horizontal asymptote. So we get a graph that looks kind of like this. All right, that one was complicated. Any questions on that one?
I just have a quick question between I mean just regarding extrema. It's between finding relative min and max versus absolute min and max. So
Yep.
for absolute min and max, do you just find the critical point and then the endpoints, or if it doesn't have a bound, and then just plug it straight into the original function
Yep.
and find it that way?
Yes,
And then,
because we have a closed interval, one of the endpoints could be the highest value or the lowest value. So it's not good enough to just look at the critical points. We also have to look at the endpoints. So that's why a better bet is to set up a table like this and look at the endpoints and critical points, and then we're just comparing the highest and lowest points.
okay. And then for relative extrema, you have to do the actual first derivative tests and plug in values in between the critical points, right?
Yep, to figure out where it's increasing and decreasing.
Okay.
Okay, let's move on now to number 8. Find the relative extrema and inflection points. Okay, so before I start differentiating this thing, I'm going to rewrite it as x squared minus 4 to the 1/3 power. So now when I take a derivative, the 1/3 comes down. I take 1/3 and I lower the power by 1, so it'll be a negative 2/3, and then multiply by the derivative of the inside stuff. Okay, I'm going to rewrite this in a way that looks nicer for doing algebra stuff. So this negative exponent, I'm going to put all this in the denominator as a positive exponent. So we have the 2x on top, and then we have 3 times x squared minus 4 to the positive 2/3 power on bottom. Okay. So to find maxes and mins, I want to look for where f prime is 0 or undefined. And then we're going to do that first derivative test. So f prime is going to be 0 when, since it's a fraction, when the numerator is 0. Look at x equals 0. It'll be undefined when the denominator is 0. So I get 2 and negative 2. So I plot all of my critical points on a number line, and then we'll go ahead and test into f prime. So try f prime of, say, negative 3. So in the numerator I get negative 6. The denominator, negative 3 squared, is 9, minus 4 is 5. 5 to some power is positive, times 3 is a positive. So I have a negative over a positive, which is negative, so it's decreasing. Okay. Again, you could just plug into your calculator and get a number, but we're just looking for the negative and positive. So I put negative 1 in, I'll get negative 2 on top. If I put in a negative 1, I'll get 1. Look at this one. 1 minus 4 is negative 3. To the 2/3 power will give me a positive number. Times 3 is positive. just for the benefit of writing something down. Oops, it's 2, 4. Okay, so I have a negative over a positive that's negative, so it's decreasing here also. Okay, we'll put in f prime of 1. When I put 1 in, on the top we get 2. On the bottom, 1 squared minus 3 is negative 3, but to the 2/3 power is positive, and then times 3 is going to be the same, 6.24. So I have a positive now, so that's increasing. And then finally, f prime of something bigger than 2, try 3. I get positives in both top and bottom, so it's increasing there too. So I only get a change at 0. Now, 0 is not defined in the derivative, but 0 is defined in the original function. So I'm going to say that's okay then. 0 is a relative min. And we don't have a relative max. All right. Now let's look at a second derivative. So I have this simplified first derivative. To find my second derivative, I'm going to use the quotient rule. So we have the derivative of the top times the bottom left alone minus the top times the derivative of the bottom. So we have 3 times 2/3 x squared minus 4 to the negative 1/3 times the derivative of the inside stuff. And all of that is over the bottom. Squared. Okay, so I think it's going to be helpful to simplify this a little bit. So I'm going to go ahead and simplify. Okay, so 2 times 3 is 6. And then I have an x squared minus 4 to the 2/3 power. And then I have minus, okay, this 3 and divided by 3 cancel. I have 2x times 2 times 2x will give me 8x squared. And then I have x squared minus 4 to the negative 1/3 power. Okay, in the denominator, 3 squared is 9. And then I have x squared minus 4, 2/3, and then when I square it, when you raise a power to a power, you multiply the powers, so this is a 4/3 power. To simplify this thing, what I'm going to do is I'm going to multiply numerator and denominator by x squared minus 4 to the 1/3 power, because the 1/3 will cancel this negative 1/3 power, and it will make this power over here a whole number again, so that, I can just drop the parentheses. It won't do me any favors in the denominator, but it won't really hurt either because I already have a fractional power. Okay. So when I multiply x squared minus 4 to the 1/3 times x squared minus 4 to the 2/3, I'll get x squared minus 4 just to the power of 1. And x squared minus 4 to the negative third times x squared minus 4 to the positive third will wipe each other out. The denominator, when I multiply the like bases, I add the exponents. So 4/3 plus 1/3 gives me a 5/3 power. Okay, so one last step. I have 6x squared minus 8x squared. That'll give me a negative 2x squared. And then 6 times negative 4 is minus 24. Okay, so now I have a nice simplified second derivative. So let's look at where is the second derivative equal to 0. That's going to be where negative 2x squared minus 24 equals 0. So divide both sides by negative 2. Okay, So I get x squared is negative 12, no solution. All right, so let's look at where it's undefined. Okay, and that's going to be positive and negative 2 again, right? It's the same thing in the denominator, just a higher power. All right, so now we do our test for concavity to find our inflection points. So I'm only going to put negative 2 and 2 on here, and I'm plugging into this second derivative. And once again, I'm just going to plug into my calculator and get either a positive or a negative number. All right, so first thing I want to plug in something to the left of negative 2. I can plug in, say, negative 3. And I end up with negative 0.32. So it's concave down. Then I'll plug in, say, 0, and I get 0.26. It's positive, so it's concave up. And finally, something bigger than 2. I'll plug in, say, 3. I get the same thing as when I put in negative 3. Okay, I get a negative, so it's concave down. So both negative 2 and positive 2 are inflection points. Okay. So should have left myself a little more room for that one, but we squeezed it in there. Any questions on this one? Okay. Problem 9. All right, evaluate the limit as x goes to infinity of x squared minus 4x over the square root of 9 minus x to the fourth plus 7x. So what I said before, you can do L'Hopital's rule, but in this case it's going to be pretty messy. But what I said was, when we have these limits as x goes to infinity, if they're like polynomial-looking things, we can just divide by the biggest power of x in the denominator. So that's what I'm going to try here. I'm going to take this limit as x goes to infinity of 8x squared minus 4x. And then I have this square root. And if I just look for the biggest thing in the denominator, that looks like this thing. That looks like a square root of x to the fourth. And square root of x to the fourth is like an x squared. So in the numerator, I'm going to divide by x squared. In the denominator, I'm going to divide by the square root of x to the fourth. Because I already have a square root in the denominator, and so multiplying by something with a square root in it will allow those things to combine together nicely. Okay, so when I distribute this into the numerator, I'm going to get 8 minus 4 over x. And the denominator, a square root over a square root, I can combine that into one big square root. Okay, and then inside that square root, I'm going to split the fractions up. So I get 9 plus 7 over x cubed. All right. And now as x goes to infinity, 1 over x to any power is going to go to 0. So this is going to be 8 minus 0 over the square root of 9 plus 0. And so I get 8/3. Okay, questions on that one?
How'd you get 1 over x squared?
So I said I'm going to divide by x squared. It's the same as multiplying by 1 over x squared.
Okay.
Okay. The key was that x squared and the square root of x to the fourth are the same thing. So 1 over x squared and 1 over x to the fourth are the same value. It's just that the 1 over x squared is more convenient in the numerator, and the 1 over square root of x to the fourth is more convenient in the denominator. Okay. Problem 10, sketch a graph that satisfies all of this information. So what we're going to do, I'm going to draw my graph eventually here, but I'm going to put the increasing, decreasing, and concavity information directly below it. Okay, but we can fill in the other information first, right? So f of 0 is 3. Okay. The limit as x goes to infinity of f of x is negative 2. That tells me that at a y value of negative 2, I have a horizontal asymptote. Okay. Oh, let's be careful now. As x goes to infinity, I approach negative 2. So as I go to the right, I approach negative 2. As x goes to negative infinity, I approach positive 2. Okay. And then at x equals 3, and at x equals negative 3, we have vertical asymptotes. Okay. Now let's fill in our increasing and decreasing information. For the increasing and decreasing, f prime is less than 0, so it's decreasing when x is less than negative 3. So it's decreasing over here. And f prime is greater than 0, so f is increasing when x is between negative 3 and 3, and when x is bigger than 3. Okay. Now, when I look at the second derivative, an x value of 0 shows up. So I want to throw a 0 in here. So maybe even before I get started with the second derivative, I can split this up and say, oh, okay, throwing a 0 in, but it was increasing from negative 3 all the way to 3. Now, f double prime being negative means that it's concave down when x is less than negative 3, and also when x is between negative 3 and 0, and also when x is greater than 3. And f double prime is positive, so it's concave up when x is between 0 and 3. Okay, so now we're going to go ahead and sketch our graph. I like to start with a point on the graph that we actually know, so this y-intercept is a good place to start. And from 0 to 3, moving to the right, it's concave up and increasing, so that's this shape. And I want to start at this point, and I want to approach my asymptote going up. If I keep moving to the right, it's concave down. I want the increasing side of concave down, so that's this shape. And I need to approach my two asymptotes. So if I go above my horizontal, I won't be able to approach it because I'm going to keep going up. Okay, so I need to stay below it and have that shape. Okay, moving to the left between negative 3 and 0, it's concave down and increasing, so I want the increasing side of concave down. I need to hit this point, and as I move to the left, it's going to slope downwards, and I need to approach this asymptote. Okay, don't worry about the horizontal asymptotes, those are only for the end behavior. All right, and then finally, from negative infinity to negative 3, it's concave down and decreasing, so I have this shape. And again, I need to approach both asymptotes. All right, so this is what a graph would look like that satisfies all of these criterion. All right, problem 11. Find a point on the parabola y squared equals 2x that is closest to the point 1, 4. So I'm going to start by drawing a graph of this thing. Y squared equals 2x is a parabola that opens sideways. If I plug in 1 for x and 4 for y, I don't get a true equation. So I know that 1, 4 is not on the parabola. It doesn't really matter where it is, but I know it's not on the parabola. And what I want to do is find a point that is on the parabola, I'll call it xy, that is closest to 1, 4. Okay. There's actually more than one way to go about this problem, but I think that we'll just stick with the easiest way, which is to say closest means I want to minimize a distance. Okay. Another way to go about this problem, though, is to say, well, I know that the distance between 1, 4 and this point will be closest when this tangent line is perpendicular to the line that joins them, but that gets complicated, so we're not going to look at that. It's complicated to set up. I don't know how hard it is to solve. I don't think I've actually solved it for this one. So let's go ahead and just focus on closest is referring to distance, so I'm going to write the distance formula. If you don't know the distance formula, then you just set up a triangle between your 2 points where the distance is the hypotenuse, one leg is a change in y's, the other leg is a change in x's, and you get back to the same spot. Okay, so the distance is the square root of x minus 1 squared plus y minus 4 squared. Okay, I have 2 variables here, and I need to have just one, so I need to eliminate a variable. So what I'm going to do is I'll go back to my y squared equals 2x and solve for one variable to get rid of it. So 1/2 y squared equals x. So I'm going to replace the x with a 1/2 y squared. Okay, now I'm going to do this problem the long way. The shortcut is to say if I want to minimize distance, that's the same as minimizing distance squared. It'll occur at the same point. So I could call my function d squared, which doesn't have a square root on it, and use that for finding derivatives. But if that seems weird or confusing, you don't need to do it, and I'll just solve it without doing that this time around. Okay, so this is my objective function that I want to minimize. So f of x, it's f of y. So now I'm going to differentiate it. So I have stuff to the half power, so we get 1/2 inside stuff to the negative half power times the derivative of the inside stuff. Okay, so let's go ahead and take care of that derivative of the inside stuff. So when I differentiate this first term, I'm doing a chain rule. The 2 comes down, 1/2 y minus 1 to the power of 1 times the derivative of the inside. And over here, 2 comes down, y minus 4 to the power of 1, and the derivative of the inside stuff is 1. Okay, so let's do some simplifying. 2 times a half cancels, so I have 1/2 y minus 1. And then over here, distribute, and I get plus 2y minus 8. Denominator, I've got this 2 times this big square root. To find critical points, I need to figure out where the derivative is either 0 or undefined. So let's look at where f prime is equal to 0. So I have 1/2 y minus 1 plus 2y minus 8 equals 0. Okay, so 2y plus 1/2 y is 4/2 y plus 1/2 y is 5/2 y. Okay, add 1 and 8 to both sides, so I get a 9. So multiply both sides by 2/5. I get y equals 18/5. I don't think that's right. Did I make a mistake? Oh, I did. Back up a little bit. This was just a copy down error. X is 1/2 y squared, and I wrote 1/2 y. Left off my squared. Okay. So let's just see if we can fix this a little bit. All right. 2 comes down. When I take the derivative of the inside, 1/2 y squared. When I bring the 2 down, I'll get 2 times 1/2 y, which is just a y. Okay. So when I distribute the 2y times 1/2 y squared, the 2's cancel and I get a y cubed. And then 2 times y times negative 1 is minus 2y. Okay. Now when I set the numerator equal to 0, negative 2y plus 2y is 0. So we just get y cubed minus 8 is 0. Y cubed equals 8. So y is the cube root of 8, or 2. Okay. Let's look at where f prime is undefined. Right? There's an easy and a challenging way to do this. The easy way to do this is to notice that this square root, right, you know, it's the same as this square root, which is the distance. It's going to be undefined when my original distance is 0. And that can't happen because 1, 4 is not on the parabola. Okay. All right. Otherwise, you end up with, you know, setting all the stuff inside the square root equal to 0. It just takes a little while to figure out, oh, that's not going to work. When you do that, I guess it shouldn't take that long. I have something squared plus something else squared, so you can't add two things that are non-zero, get 0. Or sorry, two things that are not negative. Okay, so y equals 2 is my only critical point, so that's got to solve the problem. Okay, so I just need to go and plug in x. X is 1/2 y squared, which is 1/2 times 2 squared, which is 2. So the point 2, 2 is closest to the parabola. Okay, any questions on that one? So the lesson there is don't make a mistake. All right, let's look at problem 12. Find the area of the largest rectangle that can be inscribed in a semicircle of radius r. So I'm going to put these in a coordinate plane. I want a semicircle of radius r, so we're going to just take a circle, pick the top half. radius r. And then we're going to draw in a rectangle. It's the largest possible, so it makes sense that it would hit the edges. Okay. And the way that I can think of choosing the rectangle to draw, I know that I'm going to draw a rectangle that's going to hit the semicircle somehow. So just say pick this corner and I can slide it around, right? So like if I slide it over to here, I would have, you know, a rectangle that looks like this. Okay. If I were to slide the point like up to here, I would have a rectangle that looks like this. Okay, there's a bunch of stuff on here, so I'm going to clean that up. But the point is that if I let this be a variable, I can move it around and I can try to find the rectangle that has the largest area. Okay, so I'll just call this point x, y, and think of that as being my variable. Okay, so my goal is to maximize the area. Okay, so I'll just write area is length times width. Okay. So here's the width, here's the length. The length is just equal to this y value. And the width, well, I know from here to here is x, and since, you know, circles are symmetric, right, this will be negative x. So this distance is also x, so w is 2x. So the area is going to be y times 2x. That's still two variables, though, so I'm not really in good shape yet. But I do know that this xy point hits the circle, and points on the circle satisfy the equation of the circle. So I find the equation of the circle. You say, okay, equation of the circle, it's a circle of radius r centered at 0, 0, so its equation is x squared plus y squared equals r squared. Okay, so x, y have to satisfy that equation also because the point x, y is on the circle. So y squared is r squared minus x squared. So y is the square root of r squared minus x squared. Okay. So I can rewrite my area function now as 2x times the square root of r squared minus x squared. And r isn't really a variable, right? It's an unknown constant because the semicircle has a radius r. We just aren't told what that radius is. Okay, so we have a function of one variable now, so we can differentiate it. So I'm going to use the product rule because I have a product here. So the derivative of 2x is 2 times this square root left alone. Write it as a half power plus 2x left alone times the derivative of that square root. So the half comes down, r squared minus x squared over the power by 1, so it's a negative half, times the derivative of the inside stuff. R is a constant, so the derivative of r squared is 0, and the derivative of negative x squared is minus 2x. Okay, so we have 2 square root r squared minus x squared minus 4x squared over the square root of r squared minus x squared. That's our derivative. Okay, now I'm going to go ahead and just simplify here. I really like having my derivative as one big fraction so that when I set it equal to 0, I can just look at the numerator, and when I look for where it's undefined, I just set with the denominator equal to 0. So I'm going to get a common denominator. So I'm going to multiply by the square root of r squared minus x squared on top and bottom. Okay. So I have 2 times r squared minus x squared now without the square root minus 4x squared over the square root of r squared minus x squared. And since we're simplifying, we'll go one more step. So I have 2r squared minus 2x squared minus 4x squared is a minus 6x squared. Okay. So now if I look for where a prime is equal to 0, I will get 2r squared minus 6x squared equals 0. So 2r squared equals 6x squared. Solving for x. So 1/3 r squared equals x squared. Oh, made another mistake. I need to be more careful. 2x squared times negative 2x squared is a negative 4x squared, but then I left out this half. Let's just fix that. So negative 2x squared minus 2x squared is a minus 4x squared. Okay. Not a drastic difference here. Still the same stuff. It's 4x squared, 4x squared, so I divide both sides by 4. 2 divided by 4 is 1/2. So when we square root, I will get a positive minus root of 1/2 times r, but I don't want the negative one because I don't, want to worry about x being negative. It's kind of all the same. That would just be a point over here, but we're just going to use x equals positive square root of 1/2 times r. Okay. All right, now let's look for where a prime is undefined. So that's where the square root of r squared minus x squared is equal to 0. I'm solving for x. So that's where r squared minus x squared equals 0. So r squared equals x squared. So x equals r. If x equals r, then y is the square root of r squared minus x squared, which is r squared minus r squared, which is 0. And so then the area is 0. So even without checking like second derivatives or anything like that, I can see, oh, area being 0, that's going to give me a minimum, not a maximum. So that's not the one I want. This is the critical point that I want. Okay. So x is the square root of 1/2 r. So then my area, yes, let's find the area. So then I'm going to look at my area function. So that's 2 times x, so 2 times root of 1/2 times r. And then I have the square root of r squared minus x squared. Well, x squared I know is 1/2 r squared. R squared minus 1/2 r squared is 1/2 r squared. Square root of 1/2 r squared is the square root of 1/2 times r. Square root of 1/2 times the square root of 1/2 is 1/2, times 2 is 1. So we're just left with r squared. All right, that one is complicated. Any questions on that one? All right, let's look at problem 13. Man launches his boat from point A, and we're given a diagram. So starting here, the bank of a straight river, the river is 3 kilometers wide. He wants to reach point B, and we're going to either row straight across to C and then walk down, row the whole way, or we could angle it and go from A to D and then walk from D to B. And if I think of that point D as being a variable, we could allow D to slide all the way up to C or all the way down to B, right? So it gives us some options. All right. Where should he land to reach B as soon as possible? So if I say that this X is how far downstream, find X that minimizes the time it takes. Okay, so I'm going to write a function for time. So we have the time on the water plus time on the land. Okay. Time on the water, well, so if we think about speed or rate, it's distance over time. If I solve for time, time is distance over rate. Okay. So the time on the water is the distance over the water. I'll give that a variable, call that y. Divided by the speed in the water. Well, you can row 6 kilometers per hour. So I'm going to divide by 6. Time on land is the distance over land. Well, this is the distance over land. So I have this whole distance is 8. Take away x will give me the remaining distance. So 8 minus x divided by the speed on land, which is 8. Okay. So this is 1/6 y plus 1/8 times 8 minus x. All right. We have a function of 2 variables. We need to eliminate a variable. So what I'm going to do is come back here and find a triangle somewhere. And if I label the sides of this triangle, I have x, I have y, I have 3. So if I use the Pythagorean theorem, 3 squared plus x squared equals y squared, and then I can eliminate a variable. So I'm just going to eliminate y because that's just one step, square root both sides. So y is the square root of 9 plus x squared. So I'm going to plug that in for y. So I have 1/6. Instead of writing it as a square root, I'm going to write this as a half power. So 9 plus x squared to the half power plus, if I distribute this eighth, I'll get 1 minus 1/8 x. And we're ready to take a derivative now. So t prime at 1/6 times 1/2, 9 plus x squared to the negative half times 2x using the chain rule. The derivative of 1 is 0, and the derivative of negative 1/8 x is minus 1/8. Okay, so that's our derivative t prime. Now we want to figure out where is t prime equal to 0, and where is it undefined. So maybe let's rewrite this really quickly. 1/6 times 1/2 is going to be 1/12. And I'll put this in the denominator as a square root. And then we have this 2x. Could have maybe canceled this 2 and the half. Maybe keep my numbers a little bit smaller. So now I just have a 6 in the denominator. And we have an x in the numerator. Okay. And just like I did in the last problem, or a couple problems ago, I said I like to write my derivative as just one big fraction. So I'm going to get a common denominator. So I'm going to multiply by this square root on top and bottom. Okay. 6 is 2 times 3. 8 is 2 times 4. So I need an extra factor of 4 here and an extra factor of 3 here. So we have 4x minus 3 square root 9 plus x squared over both of these, 4 times 6, 8 times 3, they're both 24. Okay, so that's our nice, neat common denominator. So let's look at where t prime is equal to 0 and where t prime is undefined. It's going to be undefined when the square root of 9 plus x squared is 0, which will happen when 9 plus x squared is 0, which will happen when x squared is negative 9, which has no solution. Okay. T prime is equal to 0 when 4x minus 3 square root of 9 plus x squared is equal to 0. So if I add, I get 4x equals 3 square root 9 plus x squared, and now I'm going to square both sides. So on the left, I square the 4 and get 16, square the x and get x squared. On the right, I square the 3 and get 9. I square the square root and it goes away. Okay. So distributing on the right, we get 81 plus 9x. Okay, so 16x squared minus 9x minus 81 equals 0. And we have a quadratic. So x equals the opposite of negative 9, plus or minus the square root of negative 9 squared, minus 4 times 16 times negative 81, all over 2 times 16. And I'm going to run this through my calculator really quickly and just write down the decimal approximation. Okay, so I get two values. X could be 2.5488, or x could be negative 1.9863. But going back to my diagram, it doesn't really make sense for x to be negative, because then he would be going away from his ending point and then walking further. That's clearly not a solution. Okay. So I just want this x value. We're still not sure, though, is that the best option straight across, or is straight down the best option? So what I'm going to do here is I'm going to compare them all to each other. So I'm going to look at x values, and I'm going to look at time. So straight across would be an x value of 0, and straight down would be an x value of 8. So x could be 0, or 2.5488, or it could be 8. And then what I'm going to do is I'm going to compare all of those in my function for time. Okay. So that's my function for time. So if I get out my calculator, okay, y equals, I'll plug in my function for time, 1/6 times, just write this as square root, 9 plus x squared plus 1 minus x over 8. Okay, so I go to function y1, and I'm going to plug in when x is 0, plug in when x is 8, and I want to plug in when x is that critical number I got, 2.5488. Okay, so 0 we get 1.5 hours, At 8, we get 1.42. And at our critical point, we get 1.3375. And we're looking for the least amount of time, so that's it. Okay. All right, moving on. Problem 14. A metal can is to be constructed with a volume of 100 cubic inches. The can is a right circular cylinder. If the cost of the metal for the sides of the can is 4 cents per square inch and the cost of the top and bottom is 5 cents per square inch, find the cost of the cheapest such can. Okay, so for my diagram, I've got a cylindrical can. Okay, some radius r, some height h, and what I want to do is build a function for cost. So I have cost of the top plus cost of the bottom plus the cost of the side. Okay, so for the top, the metal is 4 cents per square inch, so I have 4 times the area of the top. For the bottom, it's 4 cents per square inch, so it's 4 times the area of the bottom. And for the side, it's, oh, I have that mixed up. The side is 4 cents, the top and bottom is 5. Okay, so for the side, it's 4 times the area of the side. Okay, to find the area of the top, that's a circle of radius r, so it's pi r squared. Same thing on bottom. For the side, if you were to unroll it, you get a rectangle where one dimension is h and the other dimension is the circumference of that circle. Circumference is 2 pi r. Okay, so my cost equation is going to be 10 pi r squared plus 8 pi r h. This is a function of two variables, r and h. So we need another constraint to eliminate a variable. And so we're going to use this other piece of information. The volume is 100. Okay. The formula for volume of a cylinder is pi r squared h. Okay, so I want to eliminate a variable. So I'm going to solve for h to eliminate it. So h is 100 over pi r squared. And I can plug that in for h over here. So 10 pi r squared plus 8 pi r times 100 over pi r squared. And now we'll do a little canceling. Pi's will cancel. One of these r's will cancel. So I have 10 pi r squared. 8 times 100 is 800. And I'm dividing by r. I'll write that as an r to the negative 1 power. So now we have cost as a function of one variable r. So now we look at the derivative. C prime of r. I get 20 pi r minus 800 r to the negative 2. Okay. It's going to be undefined, so r to the negative 2 is a 1 over r. It's going to be undefined when r is 0. When r is 0, we don't have a can, so that's not a real solution. Okay, so I'm going to look at C prime equals 0, so 20 pi r minus 800 over r squared equals 0. And we just said that r equals 0 is not a solution, so if I don't have to worry about r being 0, I can multiply through by r squared. That will eliminate my fractions. So we have 20 pi r cubed minus 800 equals 0. And now we just isolate the r. So 20 pi r cubed equals 800. Divide both sides by 20. So I get pi r cubed equals 40. R cubed is 40 over pi. So r is the cube root of 40 over pi. And that comes out to 2.335. Okay, the goal of the problem was to find the cost of the cheapest such can. So I'm going to go back up to my cost equation and plug in for R. Okay, so I have 10 pi times my 2.335 squared plus 800 divided by the 2.335. Okay, so we get 513.899, and my units here, the sides were written in cents, so this is cents. Okay, or we can write it in dollars as $5.14. Okay. All right, let's keep plodding on through. I think that was it for the long story problems. So hopefully this will speed up a little bit. All right, so let's do some L'Hopital problems. Find the limit as x goes to 0 of 1 minus ln of x over, oh, actually we did this one in class, so we'll skip 15. 16, x is going to infinity, x squared plus 4x over e to the 3x. So I'm going to try direct substitution. I get infinity plus infinity over infinity. So that is the right form for L'Hopital's rule. So I'm going to get a new limit as x goes to infinity. When I take the derivative of the top, I'm going to get 2x plus 4. When I differentiate the bottom, I get e to the 3x times 3. Try direct substitution. I get infinity plus 4 over infinity. Okay, infinity plus 4 is still infinity. So I'm going to use L'Hopital's rule again. Okay, so when I take a derivative on the top, I'm just going to get 2, right, plus 0. On the bottom, I'm going to get e to the 3x times 3, and then I have this other 3 hanging out. And now as x goes to infinity, I'm going to get an infinity in the bottom, but just a 2 in the top. And if I have a limit where the denominator is going off to infinity, the numerator staying fixed, and dividing by bigger and bigger numbers, that's going to go to 0. So the limit as x goes to infinity, x squared plus 4x over e to the 3x is equal to 0.
How did you differentiate e to the 3x? Can you just show that?
Yeah. So derivative of e to the x is e to the x. So the chain rule, if I have some function of x, the chain rule says do your derivative like normal, and like normal means nothing happens. Make sure you plug in the inside function, and then you multiply by the derivative of the inside function. So if I'm taking the derivative of e to the 3x, 3x is my inside function. So when I differentiate it, I get e to the 3x times the derivative of 3x.
Okay, thank you.
Okay, problem 17. If I try direct substitution here, And I have to be a little bit careful. For this first one, I've got negative infinity cubed, which is like a negative infinity. And for the second one, we have 5 minus x. Well, if I plug in a negative infinity, it's minus a negative infinity. So I have like an e to the infinity, which is infinity. So infinity times infinity is not a, you know, that's not an indeterminate form. That's just going off to infinity. So, well, negative infinity because of the other one. So this limit is just equal to negative infinity. Okay. Now, if you want to make this a little bit more clear, right, if you look at this and it looks like I just did some voodoo, another way to look at this, to try and break some things apart so that we're not dealing with as much at once. This e to the 5 minus x I can write as e to the 5th times e to the negative x, and I can get a fraction going now because I can put this e to the x in the denominator, and I have x cubed times e to the 5th in the numerator. And now when I try direct substitution, okay, e to the 5th is a constant, so that's not going to do anything much. Again, x cubed, as x is going to a negative infinity, I'm going to have a negative infinity cubed, so that's a negative infinity. But if I look at the graph of e to the x, as x goes to negative infinity, e to the negative x goes to 0. So I've got like an infinity over 0, or another way to look at this is a 1 over 0, which is an infinite limit, times infinity, which is an infinite limit, right? So they're both sort of pushing me off to infinity, right? Except I have a negative, so it's a negative infinity. Okay. That one is like short because we don't actually use L'Hopital's rule, but I feel like it's confusing, which is why we're looking at it. Any questions on that one? Okay, let's go on to 18. Was 18 the one we did? I think we did 18 in class. So I'll skip to 19. Use Newton's method with an initial guess of 1 to find an approximation for the absolute minimum of this function, right? So I want to find the minimum of this, and in order to do that, what I'm looking for is the critical points. So we look at f prime of x, 4 comes down, and I want to figure out where this derivative is equal to 0. So I have x cubed plus 2x minus 3 equals 0, and that's a cubic, and that's where I run into a problem, and that's why I want to use Newton's method, because we don't have a nice formula for cubics. Turns out there does exist a nice formula for cubics like there is for a quadratic, but it's not as nice. If you think of the quadratic as being a little bit painful, the cubic formula is like 10 times more painful. And there's a bunch of like cases and stuff, so it can get pretty complicated. That's why you don't bother with it. Okay, so this is the function that I want equal to 0. All right. F is already taken, so think of this as being like maybe my g function. So g prime is 3x squared plus 2. So in my Newton's method formula, I want my previous guess minus g of the previous guess over g prime of the previous guess. Okay, so my formula is going to be xn minus xn cubed plus 2 times xn minus 3 over 3 times xn squared plus 2. Okay. So I'll get my calculator. Oops. plug that in as a function. So x minus the numerator, I have x cubed plus 2x minus 3 divided by, and in the denominator we have 3x squared plus 2. Okay, variables, y variables function, y1. My initial guess, we said was 1. Oh, and 1 solves that. Okay. So, when x0 is 1, my next guess is also 1. So 1 is an exact solution, and actually if you look at f prime, so it happens that if we plug in 1, we get it exactly. Okay. So this one, we used Newton's method, but it turns out that our guess was a lucky guess and landed exactly on the correct solution. Okay. So that's it. If we want to write this out neatly by hand, x1 would be 1 minus 1 cubed plus 2 times 1 minus 3 over 3 times 1 squared plus 2. And we get 1. Okay. Okay. That was the only. We're not going to bother to like look for other minimums and stuff because this is the only guess that they gave us. So if there are other solutions to f prime equals 0, that you're not going to have to like pick your own initial guesses for Newton's method. All right, problem 20. Find the antiderivative. That one we did. Okay, so let's look at the antiderivative of this one. We don't have a product rule for antiderivatives. So what I need to do is first algebraically do something so that I don't have a product anymore. So I can write this as x to the half times 9 minus 5x. And I'm going to distribute this x to the half so that I have 9x to the half minus 5x to the 3 halves. And now I don't have a product. No product, no problem. So I'm going to use the power rule for antiderivatives. So remember the power rule. If I antidifferentiate x to the n, I add 1 to the power and divide by the new power. Okay. So coming back here, when I antidifferentiate, the 9 hangs out. I add 1 to the power, so I'll have 3 halves. I can write divided by 3 halves. I prefer to write times 2/3 because that's the same thing, but then I don't have multiple layers of fractions. Okay. Constant multiple -5 hangs out. For the x to the 3 halves, I add 1 to the power, so it'll be 5 halves. Divide by the new power, or multiply by its reciprocal, 2/5. Okay, and I'll just do one layer of simplifying. 9 divided by 3 is 3, times 2 is 6. And here the 5's cancel. Okay. All right, last problem, solve the initial value problem. So we're given a derivative, and we're given an initial value of the function, and we want, our goal is to find f of x. Okay, so I can start by saying that f of x is the antiderivative of f prime of x. So I'm going to anti-differentiate 6x squared minus 10x plus 1. So I'm going to use the power rule. So I get x cubed over 3, 10 hangs out, x squared over 2. When I anti-differentiate 1, I get x, and then a plus c. So simplifying, 6 over 3 gives me 2. 10 over 2 is 5. Okay, so now I have this general solution, and I'm going to use my initial value to get the particular solution. Okay, so f of 0 equals 7. So 7 is 0 minus 0 plus 0 plus c. So 7 equals c. Then my f of x is 2x cubed minus 5x squared plus x plus 7. Okay. That's the review sheet then. Any questions?
Will you post this on Blackboard?
Yes, absolutely.
Okay. Thank you.
Anything else? Okay, well, if anything comes up while you're studying or you have any homework questions or anything, just feel free to send me an email. I'll keep an eye out for those today. I'll check again tomorrow morning early. And otherwise, I will see you for the exam tomorrow morning.
Thank you.
Thank you.